All right, folks. Couple of quick announcements before we get started with things. So, sent out kind of some notes on this first quiz. Okay. First quiz, always tough in any class because you never know what people are going to ask, how these are going to go, and things along those lines. And so, again, with multiple trials, right? With multiple having these quizzes every other week, kind of chopping things up, you'll start to get used to them. They're always going to be the same. They're always going to be kind of the same type of questions and things along those lines. So giving you lots of opportunities to start to build up your prep to focus on the types of questions and things like that that we'll be putting together here. So the one thing I'll say with this next group of modules gets into like some neuropsych stuff, which sometimes people find to be pretty tricky. In general, statistically speaking, this next quiz seems to be the most difficult of the semester, I guess, just in terms of gauging performance across semesters. So you definitely want to get on these modules early, make sure that you're taking notes. Keep in touch with me if you have any questions. Have had a number of good office hour sessions with people sort of going through looking at study materials and study strategies and things along those lines. If you want to go back through and take a look at your quizzes, you can always do that. Just get in touch with me, and what I'll do is I'll pull up your responses. We can look through them, see what you got right, see what you got wrong. I'm happy to do that with you all. Office hours are a great time to do this. If that fits with your schedule, just send me an email and I'll try and manage the queue to get people in so that we don't overlap. But if you got friends in the class and you want to join in together, that's cool too, as long as you guys are fine with it. So let me know if you want to go through. It's always nice to go through and see what you got tripped up on, to see if there's some sort of strategy or some approach that you're taking that could be improved on in any way. Okay. So get started early. Make sure that you're taking notes on lectures, on modules. If you have access to the Launchpad website, that's a nice way to go through. You can run through those learning curve activities to get some additional practice on text material. The stuff in the text is going to overlap with stuff in the lecture. So just going through that will just build you up quite a bit. Okay. So thinking about prep. Other thing too, remember that when we're looking at the syllabus, a big chunk of your grade is based on research participation. We touched on that in that first meeting, kind of talking about what that is. Again, this is 15% of your grade, and I think it's 15% of your grade. I think it's 15% of your grade. But as long as you do your research, as long as you get those 6 hours, that's 100%. Like you just like, it's like getting hundreds on everything. This semester, research, because of pandemic and shutdowns and pauses and so on and so forth, research is mostly going to be online. Usually it's a mix of online studies, some in-person studies, but this semester it's pretty much just going to be, you should probably expect it to be mostly online, which is convenient for you because you can just do these studies from the convenience of your home and things along those lines. You're going to need 6 hours, and this is not sort of me, this is just a requirement, 6 hours of research participation. And so what you'll do, I'll give you a link to a video that kind of walks you through the basics of the Sonar System website, links you in, sends you links to places that you can go to find some information on research participation. But basically, you go to the Sonar Systems website. That's going to manage your participation. You'll just go in there, you'll create an account, and then once you create an account, the email that you put in there, make sure that it's an email that you check, because any correspondence with researchers is going to go to that email address. Sometimes, if you're like me, I've got joshclapp@yahoo.com that I just send stuff to, right? But I don't check joshclapp@yahoo.com a whole lot. So I got to go through, and you want to make sure that this isn't just some random email address that you go through and don't check. Important stuff will come there. So when you go through, keep that in mind when you're creating an account. You create an account, and then what you're going to go through and do is that Sonos Systems website is going to show you what research projects are up and running, which ones you might be eligible for. You can go through, sign up, schedule appointments, manage everything on there. It's a pretty slick system and pretty self-explanatory when you get in there. So you need to go through and complete 6 hours of research. The first opportunity will come starting next Monday. What we'll have is a big pretest. This big pretest is just a big kind of online survey. It's just going to have a bunch of different questions that a lot of them aren't going to sort of be connected. This is just questions and surveys that people have come in to try and determine who might be eligible for sort of different studies that people are running. So very, very, very important. It'll take you about an hour-ish to go through that pretest. You don't have to take it, but if you do, that'll get your first hour of research out of the way. And then 2, it's going to open up opportunities for studies down the road. Okay. Now, what happens is sometimes people don't do this, and then you're like, oh, I need to get my research, but now I'm not eligible for a lot of studies because most of the studies probably need that pre-screening stuff. And if you don't have it, the number of studies you can participate in gets pretty small. Okay. So make sure, and I'll keep reminding you, that pre-screen will be up for a couple of weeks. I'll keep harassing you and say, hey, make sure you do that. Make sure you do that. It's just nice. It's online, just online surveys. Go through, work through carefully, answer honestly, and that'll get you kicked off. Okay. So, that's kind of the overview of research. Easy peasy. All you got to do is just go through. You'll find some studies are worth maybe a half credit. Other studies are worth 3 credits more. It just kind of depends on sort of the workload and the time effort that you'll be involved in that. Now, for anybody who is just philosophically opposed to participating in research, 100% understand, would never try to compel anybody to or force anybody to participate in research if they didn't want to. For those individuals, what we have is an alternative. Basically, they're just article quizzes. So if you go to the Department of Psychology undergrad research participation page, you'll find links in that video I'll send to you. All you need to do is go through, and there's different articles. You click on the article, it'll bring up the article, or you read the article, and then you let Brittany, the person who's in charge of all this stuff, let her know you want to take an article quiz, and you just go through and answer some questions about the article. Make sure that you've read it, and if you pass that quiz, then you get 1 hour of research. Okay, and so there's 6 of those over the course of the semester. If you say absolutely not at all interested in participating in research, you can take those article quizzes instead, or even if you want to do a mix and match, you can do that as well. Okay, so for our class, 6 is required. Okay, but what I'm going to do is I'll credit you up to an additional 3 hours. So if you go through, you get your 6 hours, and then you go through and you do an additional 3 hours of research, I'm going to extra credit you up for that. And then if you just go through and you don't have any unexcused no-shows, if you just show up for all your appointments and do everything that you signed up to do, that's helping us on the research side of things. I'll give you thank you credits for that, and sort of give you just an extra bonus on top of that if you don't have any unexcused no-shows. Okay, so the important thing for you all is that if you go through and you do that, this is a huge buffer for the quizzes. The quizzes are tough. I don't make these quizzes to intentionally try and trick you, but they're challenging, and I know they're challenging. But how I sleep at night is I know that a good 15% or more of your grade is going to come off of just research credits, just extra points, just free money stuff. And so this is going to be a big buffer for your stuff. So your final grade, if you get through all your research, your final grade is going to be considerably higher than your quiz average, just the way this is all put together. So there's a lot of padding going on there. Okay. Questions on that? All right, cool. So I'm going to post a link to a video. It's me narrating some stuff, so you go through, listen to that. You'll find comfort in my voice because it'll be familiar. So going through all that, and then we'll link you to a web page where you can go through, find handouts and stuff along those lines, kind of walk you through how to go get set up with a Sona account. But once you're in there, if you have any questions, obviously just shoot me an email. I'll get you squared away. Sound good? All right, cool. Let's jump into, all right, neurological systems. All right, so so this unit here, again, know that this ends up being a little bit tricky for some people who may not be biologically A&P type of oriented, physiological types of things. But so we're going to kick off sort of the actual sort of research science types of things, talking about some basic biological systems and the interface between biological systems and psychological functioning. Really, really interesting area, really, really complicated in both from a science and philosophical standpoint. Again, make sure that you're up to speed on this stuff. I don't know if it's just because the content matter or because this is the first quiz 2 is going to be the first quiz where we have a full set of lectures, a full set of modules. So again, just make sure that you're keeping up reading the book as we work through this stuff. Okay. But the good news is a lot of the stuff that we're going to go through today is stuff that you've been exposed to before. This is a high school sort of bios types of things, right? And so if we're talking about psychological functioning, and at the neurological level, a good place to start is the basic structure of our neurons. Okay, our neurons are our basic kind of our unit for neural transmission. Here we have a classic neuron. This is going to be our classic motor neuron here. So basic parts here, these things out on the end, all these little branches here, these are our dendrites. Dendrites are what's receiving information from other neurons. So your dendrites are your receivers here. Your soma, this is your cell body. Here's your cell nucleus going on here, right? So this is where all the sort of machinery is keeping the cell alive. Then you've got the axon. Okay, your axon is your primary communication cable. Axons of different neurons can be of different lengths. Your sciatic nerves, those are the ones going from like the base of your spine all the way down to your heel. Individual neurons can have axons as long as 3 feet, right? So these can be, even on individual cells, quite large. This is where your information is going to be traveling from one neuron to the next. This axon is reaching out, connecting to other neurons. This myelin sheath here, this is like an insulator, okay? Your myelin sheath, and some neurons are myelinated, other neurons are not myelinated. But this myelination, what it does is it acts as kind of an insulator. It speeds up the processing of information down these axons. So myelinated neurons will transfer information much more quickly than unmyelinated neurons. And if we get deterioration of these myelin sheaths, this is what causes different types of neurological disorders and things like that. Okay, so we got information going down your axon and ending here at your terminal buttons. Okay, terminal buttons, this is what's reaching out to other neurons in the chain. Okay, so these are going through connecting in. And this is what's connecting to adjoining neurons. We'll go through and talk about how that signal is transmitted from the end of your terminal buttons onto connecting neurons. Okay, so again, this is all probably review of high school biology. This here is a diagram of our classic motor neuron. Motor neurons are going to be involved in the contraction of muscles and glands and things along those lines. So when we think about neurons and sort of in our head, this is generally kind of what we're thinking of. Okay. Questions on the basic structure of the neurons, kind of what that is or what the different parts do.
What is the difference between the basic structure of motor neurons and other neurons?
What's that now?
The basic difference between the motor neuron and other neurons.
Motor neurons and other neurons. All right, Court, you're just setting me up for home runs here. All right. So motor neurons are a little bit different in shape and structure than some other neurons. The basic pieces and parts are all the same, okay, for the most part. But we do have different types of neurons, have sensory neurons, okay? Our sensory neurons, these are going to be things that go through and transmit information from our sensory organs, so like our eyes, our ears, our sort of all our external senses, and link things back into our brain. So here we see a sensory neuron, and let's say this is taking signals from stimulation from light from our eyes back into our brain. What we'll see is kind of more of a branching area here. You've got your soma here, and then kind of the axon running here. So it looks a little bit different than the motor neuron. We also have inner neurons. Inner neurons are structured a little bit differently, where you've got here the soma kind of in the middle with branches going out either way. And this is going to be relays, connections between, let's say, different motor neurons. So here maybe you have a motor neuron that's going through dendrites, collecting signal, running it down the axle, terminal buttons connecting to the dendrites of this inner neuron that then relays it to then another motor neuron and just sends it out. Okay, so this is just, and again, for anybody with anatomy, physiology background or any type of neuroscience stuff, just recognizing that our motor neuron is kind of the one we always think about. This is the one we see in school and think about. But the system actually has a number of different types of neurons that go through and just provide some additional flexibility and nuance in terms of how things are set up and put together. Okay. Does this help, Court? Okay, cool.
Yes, sir.
Okay, yeah. I never know. I was sort of speaking to a blank room. Maybe someone needed to get up, grab some coffee or something like that. Okay, cool. So when we're thinking about neural communication and kind of the physiology of how all this works out, looking at the axon here of your neuron. Okay, so this is this sort of guy right here. We're talking about just say, let's say a basic motor neuron. You can think about the axon of individual neurons as kind of like a hose. Okay, just think about it as a hose is a decent analogy, I feel like. So it's sort of got a tube, and what we see inside of that tube is we've got some intercellular fluid that has some negatively charged ions, okay? These are organic ions. These are negatively charged. Ion is just a charged particle, okay? So inside the hose of the axon, we have some negatively charged ions or sort of particles here. And then on the outside, right? Because you think again, think about like your brain. Your brain's not like sitting out in the air, right? It's all enveloped in, just your body fluid stuff. And this extracellular fluid, the ions and the charge of the extracellular fluid is going to be positive. So these are positive sodium ions that are hanging out here. Okay, and what we see is this potential, this change in, or the message that's the electrical signal that's sent down your axon is caused by a shift in these electrostatic forces. But at rest, when your neuron's just hanging out there, if I've got positive forces on the outside, negative forces on the inside, what are these forces wanting to do? Yeah, they're wanting to attract, right, Cade? So the positives want to come in, negatives want to go out. In this case, the outside has more force than the inside. But when everything's in a balance, when we have a situation where we have these offsetting electrostatic forces, what we have is we would say that this axon or this neuron is in a state in its resting potential. It's ready to go. It's ready to fire. It just needs to get the signal to go. Okay, so you could think about this as this is your gun. It's ready to fire. It's locked and loaded. It's ready to rock and roll. Okay. Um, questions about sort of our basic setup here and how sort of the situation that needs to be set up for this axon to transmit an electric signal down its length.
I have a question.
Yeah.
So this is the state that it has to be after a neuron fires before it can fire again, correct? It's got to reach back to the resting potential.
Yeah. No, Michael, that's again a good point. We're getting get there in a moment. I'll often say, okay, this is like you're locked and loaded, you're ready to fire. Kind of like a firearm type of thing. But I've had a student one time say, well, it's kind of more like flushing a toilet, right? Like when your toilet's ready to be flushed, you can flush the toilet. But can you flush the toilet right again afterward? No, you can't. It's got to reset. And so this is where the state in this resting potential, this is where your neuron's been reset. It's ready to go and ready to fire as soon as it gets an impulse. So the actual electrical signal, right, that goes down is created by a rapid change in this chemistry on the outside of the neuron and on the inside of the neuron, okay? Now, I'd said, think about your neuron here, your axon is kind of like a hose. Well, that's good in terms of basic structure, but the thing that we need to add to that is that if we had this hose, and this hose had a number of different channels in it, a number of different openings, okay? And at rest, these openings are all closed. What we call these in your neuron is these are your ion channels, okay? So you can think about the length of your axon as being studded with these little openings. And at rest, right here, when we have our resting potential, positive on the outside, negative on the inside, these ion channels are closed. So we've got this offsetting electrostatic force. But let's say up here, my neuron gets a signal, right? And it gets a lot of signals from a lot of other neurons. And what this does is it then says, okay, we're getting a signal collected from the dendrites. It passes it down to the top of your axon. And what happens when your axon gets that signal, it creates depolarization. And what happens is it starts at the front and these ion channels start to open. And it opens and it opens and it opens and it opens, creating a chain reaction down the axon where we get a change in electrostatic force. Okay. Before we had positive on the outside, negative on the inside, but as soon as these ion channels start to open, we get positive ions rushing into the inside of the neuron, inside of our hose, and that triggers the next one, 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 creates an electric charge that runs down the length of the axon, and this is your action potential. Okay, this is the actual signal that runs down the length of the neuron that communicates then up here to the terminal buttons to then go on and signal the next neuron. Okay, and this action potential, this is the basic unit of neural communication. This electrical signal that runs from the dendrites, that runs down the axon, this is the electricity, this is the stuff that creates, that allows us to be able, me to talk, wave my hands around, think, my heart to beat, breathing, digestion, all of this stuff based on this action potential. People kind of see the chemistry, kind of how this chemical reaction, this change in chemical forces, once we get a signal, creates this this charge, this action potential. Any questions on this? Okay, cool. So, a couple of things we need to be thinking about in terms of our neuron. This is kind of a simplification of the kind of the basic function, mechanisms, chemistry, but some things, some limitations that we need to be keeping in mind about our neurons. Every time a neuron fires, we have a refractory period. Okay, and as Michael noted, immediately following depolarization, as soon as it transmits an action potential, it's got a moment where it's not able to fire. Okay. Our neurons can't fire infinitely fast. It's got to take a quick break before it's able to fire again. And what's happening during this refractory period? all of these positive ions in our axon, we've got mechanisms to kick those positive ions back out into the extracellular fluid. And so while the neuron is pumping these positive ions back out into outside of the axon, what we have is a refractory period. It needs to wait until it is able to re-achieve that resting potential before it can fire again. Okay. So we also see that our action potential, this occurs as an all or nothing response. Okay, this means that Ramon, if I'm talking to you, just because you're sitting in my screen right now, if you're hearing my voice right now, does it sound sort of kind of medium volume voice? Just give me a thumbs up if it. Yeah. Okay. What if I start shouting like that? Did that come across louder? A little bit? Okay. So how do we understand the difference in the intensity of your experience of that volume, right? Well, we know that it's not because your axon is firing sort of with more electricity, right? That louder sound wasn't transmitted into your brain, into your perception, because your neurons were firing with higher voltage, right? This action potential is the same. It's the same voltage every single time. We don't have a weaker action potential or a stronger action potential. If it fires, it fires. If it doesn't, it doesn't. It's a binary situation. It's 0-1. Okay. So if that's the case, if let's say I have sort of put my hand over sort of near a fire, and it's kind of warm, and then I get closer and it starts to get hot and painful. Or if I hear different sounds at different volumes, or I feel different pressure at different intensities, if it's not determined through the strength of the axon or the charge of the axon, how does our body start to communicate different intensities of different types of stimuli? Yeah, okay. That's a good one. More neurons will be triggered, and what else? That's one thing. What's the other thing?
They start firing as fast as they can.
Yep, that's it. Between the rate at which neurons fire and the numbers of neurons that fire, these are the things that come through and start to communicate greater or lesser intensities of things, right? So when I was talking reasonably to Ramon, we maybe have some neurons firing sort of kind of at a sort of a reasonable rate. When I started shouting at Ramon, more neurons are firing at a faster rate, and sort of determining intensity with that stuff. Okay. So questions about sort of people kind of understand how sort of we're sort of are at the neural level, how our bodies are communicating different intensities of stimuli.
Not really a question on
Okay.
the stimuli, but just curious, like how long does that refractory period take?
Yeah, it's fractions of a second. It's able to do it really quick, right? And this is good too, because we think about, boy, if it took 3 minutes for my neurons to fire, I would like raise my hand and then I'd be kind of frozen there for a long time. This is, Cameron, when we go back through and thinking about this myelin sheath, this is part of what speeds up these neurons, is because this is like an insulator, right? And so the only place that we've got areas for the neuron to transfer positive and negative ions is at each one of these gaps here. And so instead of running down the whole thing with a myelinated neuron, we run from this gap to this gap to this gap to this gap to this gap. And so we're skipping things further, and then there's less stuff for that neuron to have to kick those positive ions back out. So it's just a much more efficient system. And that's sort of kind of the basics of how that myelination works. But that refractory period works pretty quickly. Okay. And then what we get, but you bring up a good point. So we know that with greater intensity of stimuli, we have maybe more neurons acting and more and sort of firing more quickly. But if we have this refractory period, why is our perception of life not just like a big strobe light? Because our neurons have to have downtime, and so when there's downtime, they're not sending any information, right? So how does our body adjust so that we're not getting sort of things in bits and spurts?
Doesn't it just pump the information together?
Yeah, there's some pulling the information together, and our brain does sort of knit together things. What else though is going on?
Don't neurons fire like at alternate times?
Yeah,
Like
yeah.
space between them?
Yep. We've just got hundreds of thousands of millions of neurons going on, and what it ends up being is a volleying, right? So we experience things as a smooth signal, because if the call-in neuron is sort of getting reset, the camera neuron is firing, and so we get back and forth, and so it's got some teamwork stuff. Because otherwise, if everything was firing and refractoring at the same time, I'd be at like a disco the whole time. Like sort of things would come in and out, and it would be sort of not a great experience. Okay, so we got these sort of increases in intensity, or excuse me, increases in the rate at which neurons are firing, the number of neurons that are firing, and then this continuous volley is what gives us a smooth experience of our world. Okay. Last thing to think about here is that our action potentials, and this is kind of tricky to think about, the action potentials can either be excitatory or inhibitory in their functions. Okay, so we tend to think about like, oh, if my neuron is firing, it's sort of activating me, sort of getting me up, which is true sometimes, right? So I'm sitting here waving my hands around, talking with my hands and things like that. These are motor neurons that are firing, telling me to sort of move around and things like that. But we also have neurons in our head, and as those neurons fire, they produce an inhibitory effect. Okay. So think about if I've had 1 beer, 2 beers, 3 beers, 4 beers, right? My brain is starting to shut down. I'm having some inhibition on some things that I'm supposed to be doing, right? And what we see is certain types of neurotransmitters that relay certain types of communication. Those neurons are firing, but the effect is that it has a dampening or inhibitory effect on certain types of things, okay? So we can have certain types of neurons that as they fire more, the impact is to shut things down as opposed to speed things up. So we can have excitatory neurons, inhibitory neurons, but they're all communicating their signal by sort of sending out these action potentials. Questions? Feeling all right about this? Okay. Cool.
I had one question.
Oh, yeah.
So in the reading it talked about like the threshold, and so is there always going to be like inhibitory actions being submitted or being put out there, but the excitatory is just more abundant, which is creating that threshold, or is there moments where the inhibitory effects are just there's nothing, and therefore an excitatory can just go full force without having to pass the threshold?
Yeah, Michael, that's exactly sort of where our head goes is if I'm saying like, and I think it depends on the situation, right? If I'm not moving my hand, right, I don't have an active neural signal that's telling me not to move my hand, otherwise my hand would be moving all over the place, right? If I want to move my hand with basic motor function, if I want to move my hand, I get an excitatory, acetylcholine neurons are sort of firing to let me move my hands around with stuff. And if I don't want to move my hand, then there's just not activity, right? But there are certain systems within our body. This is kind of getting wonky, but when we start to get into psychophysiology, right? Your heart rate, the rate at which your heart beats, if there were no inhibitory activity on your heart, your resting heart rate would be a lot faster than what it actually is. What we have is a parasympathetic response or parasympathetic activation on your nervous system that it's your vagus nerve, and it's kind of a brake, right? And so basically your brain is sending signals to your heart, constantly slowing it down. But as soon as that those inhibitory responses stop, your heart rate picks back up real quick. And this is just with that signal, it gives your heart a much more Because if I dump a bunch of adrenaline into your system, that's a hormone, and it takes a while for that to get in, right? But if your heart is sort of, your resting heartbeat is actually 100 beats per minute, but I have an inhibitory response, and then I just cut that neural signal off that keeps it down to, let's say, 70 beats a minute or whatever. If I cut that neurological break, what happens is my heart rate instantaneously kicks back up, right? And so it's a much faster system. And so depending on the type of system that we've got, sometimes for some neurons, if I'm not moving my arms around or I'm not talking, it's just because my brain's not sending signals there. There's no active dampening. But there are other types of systems in our in the neurological systems that are actively sort of have active dampening stuff. And then if I take certain types of drugs that stimulate inhibitory receptors, then that sort of dampens everything down. Does that help?
Yeah, thank you.
Okay, cool. So, but building off of Michael's question here, you talked about threshold, right? Important to recognize that just because if one neuron or if one dendrite gets a signal from one neuron that says, hey, go ahead and fire, it's not going to fire, right? I have to, sort of this dendrite has to get enough signals from enough neurons up here to fire. And if it doesn't, it's not going to fire. But what we see when we get this charge going down your axon, right? Charge goes down your axon. That's actually, I need to fix that. That should be circling your terminal buttons down here. So we get an action potential, hits your terminal buttons at the end of the axon, right? And what we see is a different types of transmission of signal once we get to the end, right? Through your axon, it's been electrical, electrostatic force that's run things down. When your action potential gets to your terminal buttons here, we get something a little bit different. What ends up happening is your terminal buttons don't physically connect to the axon or to the dendrites of the adjoining neurons. There's a gap here, and we talk about this as the synapse or the synaptic gap or the synaptic cleft. And so that electrostatic signal can't jump directly from the end of the terminal button onto the dendrites of the receiving neuron. What ends up happening is we get the axon or the action potential that runs down, hits your terminal buttons, and what you have here are what we call synaptic vesicles. Right, so we got a bunch of little pouches here in the terminal button, and those synaptic vesicles contain neurotransmitters. Okay, and we've got lots of different types of neurotransmitters. What ends up happening is these little packets with the little neurotransmitters hit the end of the terminal button, and what they does, the terminal button then releases the little neurons or the neurotransmitters in here into the synaptic gap or the synaptic cleft or the synapse here. And these neurotransmitters then they float around in the synapse, and what they do is they find little receptor sites. Okay, now different receptor sites, think about your neurotransmitters and your receptor sites as kind of a lock and key situation. Certain receptor sites are receptive to certain neurotransmitters. If we've got the wrong neurotransmitter sitting into the receptor site, it's not going to activate. It's not going to transfer a signal. But if we get enough of the right neurotransmitters into this synaptic cleft that lock in with the appropriate receptor sites, and enough of those get in, what ends up happening, that triggers a response in the dendrites that then creates another active action potential that sends it all out. Okay? And then once that action potential goes down, releases neurotransmitters into the synapse, there are mechanisms to go through and kind of sweep all these neurotransmitters back out, put them back into the terminal button here. It's kind of like a recycling program because we don't want to constantly be having to generate new neurotransmitters. Once that message has been signaled, we've got mechanisms go through, sweep those up, and put those back into the terminal button. And then the chain goes on and on and on and on. Right? questions about what's going on here at the terminal button, receptor site activation, things along these lines.
Isn't that how SSRIs work? Is by inhibiting that reuptake?
Yeah.
Like cycling type thing?
Yeah, exactly, Hannah. If I'm taking an SSRI, what that SSRI does is it inhibits or sort of screws around with the natural mechanisms that would sweep up that serotonin and put it back in the terminal button. And so, Hannah, what's the functional impact of that? If I'm inhibiting this reuptake mechanism, what's the functional impact on serotonin activation?
Well, there would then be more of it that would make it to receptor sites, so it would be spread through the brain more effectively.
Yep. And so what ends up happening is instead of pulling this serotonin out and sort of halting that serotonin just kind of keeps floating around out there and has the opportunity to continue to activate these receptor sites, which then goes through and sends stuff out. Exactly right. Yeah. Other questions about sort of how we go. So it's an interesting mix of neurochemical reactions, electrostatic forces that go through and actually create the impulses that go from one neuron to the next that allow us to speak, think, exist, sort of carry on life functions and all of that.
I got a quick question.
Yeah.
So for the receptor sites, I don't know if we'll get into this later on, if I'm jumping with that or not.
Mm-hmm.
So like with like certain types of drugs, can't they like activate the receptor sites as well?
Oh yeah. Ramon, you just again, I love you guys. You're just setting me up, like pitching me softballs, man. You're just like crushing it. Yeah, exactly. If you ever have an opportunity to take a class in psychopharmacology, it's fascinating, right? Because what we do is we've got, and you don't need to know. I'm not going to ask you to know all of these neurotransmitters or what they do or their function and things along these lines. This is just kind of a for example slide, right? But what we do is our body has a number of different neurotransmitters, right? And these different neurotransmitters sort of do different things. There's a lot of overlap, right? So we see serotonin impacting mood, sort of basic sort of functions, dopamine, sort of have a high like reward centers in our brain, sort of help activated by dopamine, also important for sort of smooth movement and stuff like that. Acetylcholine, this helps us with movement, so a lot of muscle activation is involved in that. We have natural opiates, we have GABA. This is an inhibitory neuromechanism going on. If I drink too much, what's happening is I've overstimulated GABA neurons and it's shutting down my brain and making me dumb. Okay. But what we see is we can have, with different types of neurochemicals and different types of drugs and agents, these different types of drugs and agents can have either an agonist function or an antagonist function. Okay. Agonist means that it increases the activation of whatever neurotransmitter that this drug is mimicking. Okay, so if the impact is to increase the activation of that neurotransmitter, we're saying that that drug is an agonist. If it decreases, if it blocks or inhibits the activation of that neurotransmitter, we would talk about this as an antagonist. Okay, so like Hannah was saying, Paxil, different types of SSRIs, selective serotonin uptake inhibitors, reuptake inhibitors. These act as a serotonin agonist because it increases the activation of serotonin in our brain, and it does that by preventing the reuptake of that serotonin. So the serotonin still hangs out in the synapse, and it continues to activate. And what we end up getting is an increased activation of serotonin in the brain. LSD, also a serotonin agonist, has a different reaction or impact on people than an SSRI, but it's still working on the same neurotransmitters. Okay, but if we go down, if we think about acetylcholine, so this is a neurotransmitter that gives us muscular movement, is important for learning and memory and things like that. Nicotine, if anybody smokes or dips or anything like that, vapes. This is a nicotine. Nicotine is an acetylcholine agonist. It increases the impact of acetylcholine on your body. Botulinum toxin. Botulinum toxin is like an intense sort of poison. Estimated a teaspoon of botulinum toxin, pure botulinum toxin, could wipe out everybody on the face of the earth. This is a acetylcholine antagonist. Okay, and so what botulinum toxin does, if I get poisoned by with this, it goes through and it blocks acetylcholine, so it shuts down my muscle movement, right? So it blocks acetylcholine, so acetylcholine can't tell my muscles to flex. What happens if my muscles can't flex? My heart stops, I can't breathe, and I die real fast, right? So again, what we see is botulinum as an antagonist to acetylcholine that drops everything down, okay? What else do we do with botulinum toxin? What is it commonly used for?
Botox.
Yeah. We're sort of shooting deadly toxins into our face. But what does Botox do?
Paralyzes muscles.
It paralyzes muscles, right? So if I got a wrinkle, right, and I shoot some Botox in there, it's preventing that muscle from acting. And so it just goes loose, and it will reduce wrinkles, right? So it's sort of fine wrinkles and things like that, right? So again, thinking about drugs as having agonist, antagonist actions, same type of thing. If we look at our body's natural opiates, heroin is an opiate agonist, right? It's a synthetic opiate, or that it mimics the activation of natural opiates in our body, and heroin will bring us down, but it's activating sort of our natural opiate systems. Naloxone, if I sort of give you a shot of naloxone, it blocks all opiate action in your body, and so that those opiates, the natural opiates, can't activate and go on. And how that actually works, as Ramon was talking about, some of these, the way at which these create agonist and antagonist reactions is super interesting, right? Sometimes what we see are like in the case of heroin, this mimics your body's natural opiate systems, and as if so I shoot up a bunch of heroin, that hits my system and activates all those neurotransmitters and just sort of heightens that your body's natural opiate response, right? But if I shoot you up full of naloxone, what that's going to do is that substance is going to go through and it's going to block up. It's going to go through and it's going to block all your receptor sites. It's not going to activate them, but it's just like putting gum in them, right? So even if I have a bunch of heroin in my body, it's not able to activate because that naloxone is going through and gumming up all those receptor sites so that it can't activate and work, right? So really fascinating how this all sort of goes back and forth. Zoe, I see you said, so if you get Botox and it goes wrong, that doesn't mean it has something to do with synapses and neurotransmitters as well. Cosmetic reaction. I don't know. Yeah, I don't know what happens when Botox goes. Well, I guess I've seen pictures of what happens when Botox goes wrong. It makes people look pretty silly. And it does sort of Botox is an empirically approved treatment for headaches. Yeah. Naloxone is kind of in Narcan. I don't know exactly what it is, but sort of the same type of thing, sort of a thing that would block opiate action in your body. Okay. But yeah, going up to Zoe's saying, I don't know. I mean, I assume that what they've done with Botox is it's not straight botulinum toxin. They've modified it so that you can't accidentally overdose and kill somebody by trying to give them a cosmetic treatment. But sort of at the molecular level, this is how this stuff is kind of working. Yeah. All right, cool. Real quick, we're going to end on just different parts of your nervous system. Now, if we're thinking about your nervous system as a whole, can split this into a number of different branches. Okay, if we think about it at the top, this is your nervous system. Okay, what we can do is we can separate your nervous system into two branches. We've got your central nervous system and your peripheral nervous system. Central nervous system is just your brain and your spinal cord. Okay. Central nervous system is all encased in bone and protective connective tissue and things along these lines. Okay. Brain and your spinal cord. Spinal cord has 4 different sections. You don't have to worry about that so much. But just knowing that if something happens to my brain or my spinal cord, I'm kind of SOL. That means bad news for me, right? And so we've got this entire system, your entire central nervous system, encased in bone, in meninges. So this is connective tissue. If we go through and think about A&P or have looked at any type of sort of bio stuff, even if we were to open up your skull, we see that your brain is wrapped in some connective tissue that protects it. Same thing with your spinal cord. If we took it out of your spinal column, we see that it's wrapped around in some of this protective tissue to make sure that it doesn't get damaged or to try and keep it from getting damaged. So your central nervous system, brain, spinal cord, everything outside of your brain and spinal cord is your peripheral nervous system. Okay? Peripheral nervous system, main function of this is to carry information to and from your central nervous system. Okay. And for those of you who are maybe physiology majors, so have had A&P classes, you might recognize that if I've got neurons that are carrying information from the body to my central nervous system, okay, we refer to these as afferent neurons. Okay. So I'm looking at the screen right now, looking at the sort of set of people to the right of my screen. Those neurons that are taking light information from the outside world, from my eyes into my brain, these are afferent neurons. Okay. If I'm rubbing my face right here, right, I can feel my beard, sort of the textures and the stuff that I'm getting from my fingertips running into my brain to be processed. These are being carried by afferent neurons. Efferent neurons, I'm not sure why we decided to call them sort of something that was almost identical, but efferent neurons are neurons that are carrying commands from my central nervous system out to my body. Okay, so me talking, so in my brain, I'm thinking about the words I'm going to say. Efferent neurons are taking that signal to my larynx, my lips, my vocal cords, things like that, that's allowing me to go through and talk things. I'm sort of waving my hand around like moron here. That's sort of my body, my brain is telling my hands to move and things like that using these efferent neurons from my brain out to sort of the universe. Okay. So this is your peripheral nervous system. So think about nervous system, central nervous system, brain and spinal cord, peripheral nervous system. Everything else, we're going to split this down into a couple more branches when we pick up on Monday. Okay. All right. Questions?
So, this is one about neurotransmitters.
Yeah.
Isn't caffeine an antagonist because it blocks adenosine, or is it something else?
I'm not sure about caffeine off the top of my head. I haven't. Yeah, I'm not actually sure about caffeine. I think, if I'm remembering correctly, because again, this isn't my area, I'm not a neuropsychologist, but I think caffeine's kind of complex. I think it has excitatory and inhibitory functions both. I think. Let me.
Adenosine, it's an antagonist for sure.
What's that, Samantha?
For adenosine, it's an antagonist for sure.
Okay, so
That's what I know about caffeine.
That's what I was thinking.
okay, so it's an antagonist. And what is adenosine? What is it? What does that neurotransmitter do?
Adenosine puts you to sleep.
Oh, okay.
It's like it's how you know when you're tired, because when you wake up, it slowly builds and like makes you want to go to sleep at night.
Okay, yeah. Okay, that makes some sense, right? So again, that would be a good example of a neurotransmitter that has an inhibitory function, which makes some sense, right? Like if I'm trying to go to sleep, it's not just like my body shuts down and stops working for a bit, right? We've got natural inhibitory responses in the brain that go through and shut systems down, right? So yeah, that's a good example. Samantha, thank you for jumping in on that. Yeah. Other questions?
I also noticed there's some questions in the chat too.
Oh, yeah. Oh, yeah. Sorry, sort of touched. We got on those sort of kind of. I'll go through. I'm interested to see what happens if I got too much Botox. What that what that would do to my system. So, and what's in Narcan, I'm not sure. I mean, but again, so I've done some research in sort of pain management and stuff like that, because it's often something that comes along with trauma. And I've gone to a couple of medical conferences before. And so the chemistry that's put together to try and set up some of these like pain medications so that people can't go through and abuse them, it's really, really interesting at the chemical level, some of the stuff that they're doing. So, for example, there are certain like opiates and pain medications so that contain like trace levels of, what was it? I think like some sort of actual like pepper sort of thing that will make you, if I eat too much of it, it's going to make me sick. But if I take the level that I'm supposed to, then I'm fine. And so some of the mechanisms that people try and do to go through and counteract some of the potentials for abuse with some of this stuff is pretty cool. So, all right. Any other questions?
Medications, that's like the same thing.
What?
ADHD medications, like, it's basically amphetamine, so they add
Yeah.
stabilizers and stuff that make them act really slow, so you can't just abuse them.
Yeah. Yep. And if you do any type of bio stuff or have an opportunity to take a psychopharmacology class, that was one of the most interesting classes I took. So, I mean, they're just medications and substances abound, right? To try and get drugs and behavior is another good class to take if you find this kind of thing interesting. So it just talks about how sort of these substances that we've developed and these compounds we've developed goes through and actually impacts sort of the system and how it does, and how it all works together. It's pretty cool. Yeah. All right. Any other questions, folks? Okay. Cool. What I'm going to do is I'm going to send out an announcement. You guys are probably about over announcements from me, but go through, read them, because they're important. It's kind of the best way to go through and communicate with folks. What it'll be is for the research stuff. So go through, log on to Sona, create an account, easy. You're probably not going to see, there's not going to be anything there for you to participate in right now. And that's just because we won't have things up and running. Now, after Monday, there might be a couple projects up that you can participate in. So if people have studies that don't require the pre-screening information, and there's probably going to be some of them out there, those will be able to start right away on Monday. And so just go through, check this stuff to go through and sort of keep up. Get your participation out of the way early. Again, 6 hours is what you need. I'll credit you up to 9. If you go over 9, I can't credit you over that, but sort of if you wanted to do that, that's sort of, it's a free country. You can do whatever you want. But that's going to be a huge buffer on your scores. Okay. So, go through, take a look at that. Let me know if you have any questions. And otherwise, enjoy your weekend. What's that?
What is that background type of test? Like the thing
The screening test it'll be up next Monday. So it'll kick off on Monday, and it'll continue on for a couple of weeks. I'll harass you to sort of go through and take it. It's just important that people do it, because otherwise, at the end of the semester, I get people who are like, "Oh, I don't have any studies that I can participate in." I'll say, "Did you participate did you complete the pretest?" And no, and so then that sort of makes them just automatically ineligible for things that they might have been able to take before. Okay. Cool. Any other questions with any of this? Awesome. All right, folks. Cool. Enjoy your weekend. Stay healthy, stay safe, and we'll catch you on Monday. All right. We'll see you.